You're listening to Conferences Online Allergy from Children's Mercy Hospital in Kansas City, Missouri. Today is September 22nd, 2023. Our topic is Artificial Intelligence in Healthcare, presented by Dr. Nicholas Reiter. He is an Associate Professor of Pediatrics and Allergy Immunology at Liberty University College of Osteopathic Medicine. He is also the Chair of Clinical Informatics at LUCOM in Lynchburg, Virginia. So you're listening to Conferences Online Allergy from Children's Mercy Hospital in Kansas City, Missouri. Today is September 22nd, 2023. We have Dr. Reiter here today. He's presenting on artificial intelligence in healthcare using computational approaches to improve IEI patient care. Dr. Reiter is an Associate Professor of Pediatrics and Allergy Immunology at Liberty University College of Osteopathic Medicine, also known as LUCOM, and a practicing clinical immunologist at Collaborative Health Partners in Lynchburg, Virginia. He serves as the chair of the LUCOM Division of Clinical Informatics, which engages in research, education, and in the development of a learning health system along the Blue Ridge Mountains of Virginia. Dr. Reiter also runs Chili, the Computational Human Immunology Lab and Innovation Hub at LUCOM, which focuses on using clinical data science approaches to understand health disparities, track quality, and improve healthcare outcomes. Thanks for joining us today.
Oh, thank you, Tal. And it is not June 22nd, forgive me. And Tal and I were just talking that we put her back as a first-year allergy immunology fellow. So certainly we don't want to do that. So forgive me for the date error there. But it is an absolute pleasure to be with you today. I did my medical school there in Kansas City. Have a tremendous fondness for that city, that town. We were reminiscing about that. In particular, Children's Mercy did a couple rotations there. So great to be with you all today. And thank you for the invitation. These are my disclosures. In terms of what we'll talk about today, there is so much to say about artificial intelligence in healthcare, right? And just AI in general. And I think, having given this talk, I didn't give this exact talk, but having given talks like this, even in June, we're saying different things now than we would have, 3, 4, 5, 6 months ago. So I wanted to just, if you'll allow me, just do some level setting around what is AI and where are we currently in healthcare, understanding that, probably tomorrow this is outdated. And the rapid pace is just amazing, which is both exciting, but also highly disruptive for many great reasons, but also for some reasons that we really need to focus on and get our our arms around it. I'll talk about the Chili, the Computational Human Immunology Lab and Innovation Hub, and who we are and what we do a little bit, and then really spend a good bit of time focusing on our work and using artificial intelligence and machine learning to hopefully improve diagnostic rates and care for patients with IEI or inborn errors of immunity. And then talk a little bit about some of our approaches for using EHR data to understand, what features are relevant for building models and leveraging EHR systems again to call forward patients who may have these disorders. And then lastly, I'd like to talk about the context within which I think AI and ML will be best suited, and that is not in a standalone silo or even a research environment, but really within a dynamic health system, i.e. a learning health system where outcomes and improvements for patients are improved with each iterative and successive visit for that patient via analytics, AI, but certainly data structuring and process control and so forth. And then we'll wrap up. So I like to share these numbers because I think they really exemplify something that's really sobering. I often joke that this is not my gym locker combination, although it may look like it, although I don't know if gym lockers actually go up to 60, but 60, 30, 10, these are three numbers that are really relevant to healthcare and kind of underscore why we need better healthcare and perhaps point to a means by which and a focus that AI could be leveraged to improve. And the 60% is that only 60% of healthcare is in line with evidence or best practice. So we do a lot of things just because we think it's the right thing, or maybe it's cultural, how we did it in training, you name it, but it's not necessarily always in line with updated best practice recommendations. 30%, so if 60%, only 60% is in line with best practices, well, there's a significant proportion that's actually wasteful or low value care, and that's the 30%. And then lastly, roughly, or maybe a little bit more than 10% is actually harmful. And of course, these are not intentionally harmful practices. These are practices that, are maybe done out of our what we think is best, but we just don't know because there's not evidence to support it, or we're not aware of the evidence, or let's face it, we all work in very, very complicated, chaotic environments. I'm actually today in Washington, D.C. attending a conference on the future of work in healthcare and kind of reimagining spaces and processes that could improve healthcare providers' experience in the clinical setting, but also outcomes for patients. So there are a lot of balancing measures that contribute to this, despite us all being very altruistic, very hardworking, very patient-centric individuals. So, with that, how can AI and machine learning potentially make an impact around these things? Well, let's first just talk about what is AI and machine learning, because even though I know that the generation of many of people that I'm talking to right now are much more savvy digitally than certainly than I was at that stage of training. But maybe not everyone here builds machine learning models a significant proportion of their time, or thinks about these things necessarily in terms of their fundamental workings. So we think about machine learning in two broad categories. First is supervised learning. And this is where we take data, we label it. So we say, hey, these are the patients with a disease, and these are patients who are healthy who don't have disease. We label it. We train the machine to recognize features and discriminate those patients with the label, the disease label in this example, versus the controls. And then we give the machine, after training, a number of individuals or examples of data, and ask it to predict whether they have the patient has disease or not. And this is just one use case. So the ML model should be able to take the test data and discriminate, in this case, triangles from circles. So the upside of doing supervised learning, where we tell the machine what the 1 class and the 0 class is, or the disease class and the control class is that you can often get better performance out of the models. The downside is that it takes an expert to go through a laborious process of labeling the data, verifying that the data is in fact correct and the labels are correct, and so forth. So that's a very labor-intensive task. The other potential methodology is unsupervised learning, where we just say, okay, machine, here are a bunch of examples. In this case, maybe patients, maybe visit types, maybe, you name it, procedures. We ask the machine to discriminate the different elements, in this case shapes, based on just the inherent structure of the data. And this is, all of the different variables that you would feed into it. What you hope is that even though it's not labeled, that the machine learning algorithm will cluster or separate these classes distinctly, so that you could discriminate class A, B, C, D, or however many classes you might have. The upside of this is it's very quick. Typically, you don't need an expert to label the data. However, the downside is that typically performance is not quite as good as with supervised learning. And so, kind of thinking through supervised versus unsupervised, we can take it to the next level and say, exactly what kind of algorithms are typically used in healthcare, historically have been used in healthcare. And I will show you, this is a great journal, JAMA, but it's from 2018. So you will not see ChatGPT or GPT-4 on this axis, but I think it's still instructive in thinking about models. In this case, simple models. Actually, I would argue this is the most complicated model, and that is the human brain. But if you think about these different models, human decision-making, regression analyses, random forest algorithms, convolutional neural networks, and other more complicated neural networks such as GANs, along the axis of all human to all computer, and then some permutation or sharing between human and computer decision-making in between, you can kind of take a look and get an appreciation for the level of complexity of the models, and maybe how certain models may perform better with smaller sample sets, and how maybe larger, more complicated data sets may require larger, more complicated models. And so this is just a graph of a variety of different studies, where in this case, you might think about like Google diabetic retinopathy classifier would be, or Facebook photo tagger example, may require a very complicated low human intervention model to classify faces, whereas disease-specific algorithms may be, more human intervention in labeling the data, assessing the output of the model, and thinking about random forests and so forth. And then clinical wisdom, US Census mortality rate estimations, maybe this is done more with a straight up statistical approach, a more simple statistical approach, and even maybe human intuition. I'll also just pause and say that statistics is certainly the backbone of machine learning and artificial intelligence. So really all of the complicated models really involve statistics, as I'm sure you know, but sometimes simple regression analysis gets the job done, and that's all we need, and that's perfect. So enter the large language models. I know you'd be very disappointed if I didn't talk about ChatGPT in this talk, because it is all the rage, right? So ChatGPT falls into this category of large language models, and these GPT models, these generative pre-trained transformer models, are very complex. They learn from hugely complicated, diverse data sets that can be text, they can be images, they can be spoken voice, they can be structured and unstructured data of all shapes, sizes, and varieties. They're very exciting because they do learn very well from a use case to use case. So for example, I'm sure most of you have an account with OpenAI and have played with ChatGPT. You can ask ChatGPT all kinds of things, and it will learn from other use cases and other conversations and other literature, and pull that in many times with some funny errors, but many times will do very, very well. And this is really kind of underscores the ability of these models to adapt. The cool thing as well is that they can be trained in one environment or with one data set, and because they are so complicated, have billions of parameters, and have the capacity to kind of wrangle data, analyze data in unique ways and complex ways. They can be trained in one area, and then that model can be transferred to another area, another domain, and actually perform very well. So they do very, very well with transfer learning. And so some of the examples are listed here. These are all examples certainly you've heard of. And I think they're going to play a greater role in healthcare. Some recent review articles, as well as peer-reviewed articles, have really kind of showcased where they could fit into the healthcare space. And again, this is a really nice article from Nature that's published a few months back. And it just kind of underscores how generative AI can ingest a variety of different data and disparate data elements, such as text, audio, images, genomic information, laboratory information, data that's structured in graphical form and other forms. You can also mine the literature and pull all of that together, synthesize it, and then actually have a discussion with a healthcare provider based on all of that, but also relevant to the patient right in front of the healthcare provider. And so there are more and more use cases that are being proven effective, including ambient listening, where generative AI is listening to the conversation between a healthcare provider and the patient. And then you can tell the AI, please put our conversation in the element in a SOAP note format. Please insert it into the EHR for my review, and it'll do that. So you can imagine that generative AI, large language models, will potentially do a lot of positive things in terms of reducing non-value added clinical burden, and hopefully allow us to focus more time on the patients and less on the EHR. So kind of where's the current state of AI and machine learning? Again, moving target. This is another nice review article, but it's from 2019. So I think it exemplifies some of the positive impact for AI machine learning and some of the different domains, such as even embryo selection, or having a smart voice coach to help with health directions, or understanding electrolyte imbalances from an EKG, smartphone application, and so forth and so on. So ambulatory, pre-hospital care, imaging, hospital care, and so forth. All of these domains have had AI machine learning touch them, and have publications that can underscore that, as well as certainly some operational data to share that they are effective within the real world live environment. And so I think, what's exciting is that we could see these technologies make impact into these disparate areas of medicine, and also leverage this tremendous diversity of inputs that, as healthcare providers, as clinicians, as physicians, as nurses, as therapists, as APPs, we do the mental math of thinking about all of these elements in a clinical encounter, but for a single patient at a time. Could we do that for thousands of patients? And that's where potentially AI machine learning can help us do our jobs better, make predictions about outcomes for patients, even maybe predict clinical trajectories and so forth, so that we may be able to avoid suboptimal outcomes, make changes to drive towards optimal outcomes. And this is the kind of the grand hope, right? Like this is the hyperbole, this is the vision, the high level vision. But I think more and more we're seeing publications come out of this and prove it. And then also, of course, see these operational use cases advance. So in addition to AI and machine learning, algorithms in the research space, the FDA, not surprisingly, is wanting to put some guardrails around this. And so if you go to the FDA's website, you will see evidence and information about how to, at least through expert guidance and opinion, think about software as a medical device, think about the life cycle of the software, how to sustain it, when to sunset it, some of the quality tracking metrics that should be focused upon, some of the competencies in terms of human capital that should be involved in the teams that think about software as a medical device. And this is a little bit old now. This is probably about 9 months ago, but there at the time, maybe April or so, or early 2023, there were over 500 cleared AI, FDA cleared AI and ML devices. So we're going to see more and more regulation around this in healthcare to make sure that the model or the algorithm does what it's intended to do, doesn't have adverse events, and I think it'll be an interesting area to continue to follow. We focused really heavily on using these technologies to diagnose patients, and we'll talk about the why and some of the data around that. Get to the A in COLA and the allergy immunology. But if we did a simple search in PubMed, a few months back, we'd see artificial intelligence of medical diagnoses. There were over 35,000 results, and just in the year 2022, there were over 8,000 citations related to this. So there is just tremendous interest and appetite for leveraging this technology to even improve diagnoses across a variety of clinical spaces, whether it's congestive heart failure, coronary artery disease, diabetes, inborn errors of immunity, worsening asthma progression. Just the number of potential avenues to deploy and use and leverage these technologies is just almost exponential, and it continues to increase over time. So a lot of excitement in the research community, a lot of excitement in the operational community, and so forth. So kind of transitioning from that background on AI machine learning, I just want to tell you a little bit about what we do and what we've done, and put some context around this discussion. So the chili group, and you'll see the chilies here. When I was not in Virginia and I was in Texas, this was a little bit cooler, given all of the chili peppers we consumed in that state and the great tacos that we had to eat there. But chili is this multidisciplinary group that's really focused largely on building digital tools, software, machine learning models, analytical pipelines for improving inborn error of immunity patient outcomes. And this is really born out of my work as a clinical immunologist, hearing patient stories, seeing data, understanding these patients have long diagnostic odysseys, and looking to make a difference, to be frank, in leveraging healthcare data to bridge the gap around that. We'll talk a little bit about some of the data to support that claim. So the first kind of focus for Chile is just developing these models that may be very simple. Again, logistic regression classifiers, decision trees, straightforward machine learning models that assess risk, that are lightweight, they're very transparent, explainable, that can be operationalized in any healthcare setting to quality track patients or to make the diagnoses. On the other side of what we do is really building computational models that explains the why, the how, the what, that's relevant for these patients, understanding their concepts at a computational level. And the goal here is really that even if the model is very complicated and not quite explainable, although we strive for explainability, it may allow us to understand features about a given patient with potential immunologic dysfunction that goes from the clinical phenotype to the biology. And so here we're not as concerned necessarily about it being ported into an EHR system, but we're more concerned about how helpful and useful the model is at answering the questions that we're asking. And this is more of the research side of what we do. And we've focused heavily, as I've teased you with, on inborn errors of immunity. This community does not need this slide, but I like to put it in for context because the pace of single gene defects discovery in this space is just, again, exponentially increased. since the 80s. So we're understanding the genomics of these conditions with increasing rapidity. And of course, as you know, the International Union of Immunological Societies, or the IUIS, has 10 categories that span everything from T cell to B cell to combined defects in phagocyte disorders and complement disorders, the kinds of things that the fellows in the room are preparing for their boards to study so they can answer the questions effectively, but of course are also focused heavily on thinking about, as we all are, could this patient have this type of disorder, that type of disorder, and how do we conduct our workups and so forth. And we know that these conditions cause tremendous morbidity and mortality. They cause, of course, susceptibility to infection, but also pathological inflammation, immune dysregulation, and cancer predisposition. So more common than we certainly thought, more common than what we estimated when I was a fellow. Now we think these disorders, as a group, the prevalence is about 1 in 5 to 10,000 individuals. So, when you think about inborn errors of immunity, there's a major gap, and that is really solving for diagnostic delays. This is a common problem within the quote-unquote rare disease space, and I've just listed a few publications on the left-hand side of this slide, which get to, why does it take so long for rare disease patients to get an accurate diagnosis, and speaks to some of the diverse clinical features that's a challenge in recognizing these disorders. And some of the pattern recognition that's really vital to doing so. Busy primary care physicians may not necessarily be thinking about these disorders, and certainly they have many, many things on their plate to tackle. So again, one of our approaches is how do we build systems that could serve the primary care community to recognize these patients, because we know that, as is shown on the right-hand side of the slide, some of the disease-specific cohorts have shown that, for example, with CVID, it might take almost 9 years from symptom onset to time to diagnosis to get the diagnosis and have appropriate care implemented, and then 5 and 9.5 years for immune dysregulatory disorders and primary antibody deficiencies and a couple other studies. So this leads to those 60-30-10 items we talked about before: long diagnostic odyssey, suboptimal outcomes, missed opportunities for best care, and on and on and on, but essentially increased suffering, increased morbidity and mortality. So this is the gap we've really focused on in trying to use machine learning and AI to address. And so thinking at a conceptual level, there's this tight coupling between what we're learning in our field at the basic and translational level, the clinical science level, and the analytics that we're developing. So we think that the domain expertise in knowing and understanding allergy and immunology, clinical and science, is critically important in building helpful analytics. So you're probably not going to be able to get just the smartest data scientists in the world to build the best models for this particular use case. They will do a wonderful job, but if you have a group of clinical immunologists who can help them discriminate what variables are most important for model training and building, you're probably going to get a better model at the end. And that domain expertise, we believe, is really relevant. And it takes into account an understanding about the natural history and clinical phenotypes, biomarkers of relevance, genomic elements of relevance that we're learning in our field to then really identify the features that are most relevant for model building, which we believe and can show that leads to improved analytics that are more generalizable, less biased, and ultimately have better performance. Sometimes the balancing measures to that are that the models are more complex. We may deal with overfitting, where the model is trained and deployed in one setting, does a great job there, but you move it to another setting with a different data set and a different population, it performs incredibly poorly. And as these models do get more complicated, then of course we need larger processing units and increased compute. So where are we today as a community with thinking about AI and machine learning for primary immune disorders or inborn errors of immunity? Well, currently, our group and several others have really focused on ascertaining which patients may have disease via either using EHR or claims data as features, or perhaps using single nucleotide variants as features, or using flow cytometry data as features. And so this work has been done by a group in Chicago. Manish Butte's group at UCLA has focused heavily on CVID and use of EHR data. Yuval Atan at Mount Sinai has looking at predicting a variance using machine learning to predict variants that are pathogenic for gain-of-function disorders, and many other really interesting approaches towards predicting risk of disease, predicting genomic elements that underlie disease, and in laboratory phenotypes, i.e. flow cytometry, that can discriminate one IEI versus another, or IEI versus another condition entirely. So this gets to where we are, and what we've done is we've really taken this multimodal data approach. We've looked at claims data, structured EHR data, and text mining to really go from an individual, from a population, I should say, to an individual at risk to try and ascertain who may be at risk for a primary immune deficiency. And this started with the Jeffrey Modell Foundation. I'm sure that many of you have heard about the Spirit Analyzer, which is a software for primary immune deficiency recognition and intervention and tracking. And this is a claims analyzing AI that ingests a claims data attribute. These are all pre-identified, so maybe and relevant to IEI. So maybe pneumonia, meningitis, failure to thrive, so forth and so on. Historically, there had been a fixed hard-coded pre-specified weight that had been applied to the code. And then these codes would all be counted for each individual in a population. Each individual in the population would have a risk score calculated, or if they had nothing of interest, no claims of interest, then the risk score would be 0. But then they could be stratified into high risk, medium, or low risk, depending on their risk score. So Spirit Analyzer was built almost 10 years ago. Not surprisingly, the Modell Foundation and Fred and Vicki Modell were way ahead of the curve in thinking about how to find patients with PI. But until about 2018 or so, no one had actually deployed Spirit Analyzer in a real-world clinical environment. So we did a pilot study at the Texas Children's Health Plan, where I was employed at the time at Texas Children's Baylor College of Medicine, where we took about half of the enrollment of the TCH Health Plan, deployed Spirit, analyzed them for risk, and then followed up 1 year later to see of those individuals who were high risk, how many of them were actually given a diagnosis of primary immune deficiency or a diagnosis that would make you think they might have an underlying PI. So let me just walk you through the slide. We started with about 186,000 individuals, ran Spirit. Essentially 99% were deemed of no or low risk. And then we had about 2,200 individuals, or about 1% of the medium to high, or of the total population that we called the medium to high risk cohort. These were the subjects that we followed a year later. We sent letters to the primary care physicians for these individuals, let them know about the study, asked the primary care physicians whether they thought that our findings were relevant based on their knowledge of the patients, and then actually looked at the electronic health records of, in this case, about 770 individuals, or about 0.4% of the initial population. We looked at their charts. So some of these patients were not in our system, or some had very little data in our system. But ultimately, 1 year later, we found that 41 of these individuals from the medium to high risk group, or 2%, were given a diagnosis that one could consider to be primary immune disorder. And there were another 57 that had a diagnosis that you would say, hey, I'm a clinical immunologist. I'm concerned about that diagnosis. I need to work this patient up. So ultimately, we found that 5% of the population of the medium to high risk, population was at risk for a primary immune deficiency. This is our population, again, 186,000-ish individuals, highly representative of the Medicaid population of Houston, Harris County, Texas, very diverse, sex balanced, and mostly children, because again, this was at TCH. This was the PI group and some of the diagnoses that we found 1 year later. A lot of non-specific diagnoses, some specific diagnoses you see there. These were not diagnoses that these patients carried prior to our study. And this was really just a natural history study. So it wasn't that we don't think our intervention made the difference, but we're just exploring the clinical journey of these individuals and how predictive Spirit Analyzer was. This is the concerning diagnosis group and some of the conditions that we saw in patients that were not given a PI diagnosis, but that may have had underlying immunologic dysfunction. So we thought this was a valuable experience. We thought that this initial pilot study gave us enough ammunition and result that were robust enough to say, let's take this to the next step. So we went from this 1 year study to a 3-year rolling evaluation of Spirit Analyzer, where we wanted to do two things. We first wanted to follow a cohort of patients after initially stratifying them with Spirit Analyzer, at 6-month intervals. So we took 12 months of data for each individual after we already had an initial stratification. In this case, we assembled the cohort. So this is 1 year's worth of data. We did the baseline assessment and then took 12 months of data at rolling 6-month time points to understand what happened to the high-risk individuals. How about the low-risk individuals, medium to low-risk individuals, and how about those individuals with no claims of interest? What was their clinical journey? We also wanted to build a machine learning algorithm that was a second step to improve prediction about referrals for these patients. So this is our population, which was bigger than our initial pilot study, almost 130,000 individuals, very similar demographic from our initial cohort, again, taken from the Texas Children's Health Plan. We found that upon initially screening this population for risk with a spirit analyzer, that about 7 in 10,000 individuals were considered high risk. And we focused on these individuals for our machine learning approach. So this is the high level schema that we use. We took this population of about 430,000 individuals. We initially assessed them via spirit analyzer at baseline and assessed whether they were of no risk, low to medium, or high risk. If they had no or low to medium risk, we recycled them back into the population to reanalyze them in 6 months. The high-risk individuals, for the high-risk individuals, we built a secondary machine learning classifier to ascertain who would benefit most from referral to a clinical immunologist. And then we used that to focus on those individuals who would then either require direct intervention and be worked up or referred, or have ongoing evaluation. For example, some of these individuals had secondary immunodeficiency, or upon granular review of their chart, it was unclear that they had a primary immunodeficiency, so they were continued to be followed iteratively. I talked about spirit analyzer. I'd like to just spend a little bit of time talking about how we built the machine learning AI, the second step of this pipeline. We took features or clinical variables from the claims data that Spirit ingests to make its risk calculations from each individual encounter for an individual patient. We labeled those patients with either primary deficiency or medical complexity, trained our models, and then built them in this way. So we used this N by 7 dimensional matrix to assess the 12-month risk or likelihood that this individual would require evaluation by a clinical immunologist. And so the features, again, and I'm going to show these to you, are claims elements, and then the N, so that's the 7, the N is the number of encounters that these individuals have had. And our rationale was that even a patient with IEI aren't always going to have a clinical visit where there's demonstrable risk. Some of them will be doing well, but we wanted to capture that. We also felt that more encounters would provide more information about that individual and also be an important element to capture in making these predictions. And we called this a primary immune deficiency or primary immune disorder ratio, or PI ratio, allows for this kind of 12-month snapshot of risk for this individual patient. So this is how we stratified or set up our experimental model. We had 287 verified IEI patients and 612 individuals who were high risk. So they had a variety of medical complexity patients. These are patients with trisomy 21 or congenital heart disease or cystic fibrosis. These were the 7 elements that we used: the sex, the date of birth, top 2 ICD codes, top 2 CPT codes, and the paid visit amount. We used that to train 70% of this population on the model, and we used 30% to test it. And then the PI ratio was generated for the risk, the number of visits for a given individual that was predicted to have risk versus the total number of visits for that patient. So a PI ratio of 0.5 would be a patient who, for example, had 10 visits and 5 of those had significant demonstrable risk as predicted by a machine learning algorithm for risk of underlying IEI. I should say also we kept the primary immune disorder, the known IEI patients, in the mix. So we wanted to make sure and verify that our model actually ascribed risk appropriately to those individuals with PI for a couple of reasons, and I'll talk about that a little bit later. This is just a table showing you how we iterated forward with some of the models that we experimented with for that second step of our claims analysis pipeline. We used a variety of dense neural networks with a single layer and 128 nodes, a couple layers, 128 nodes, a couple layers of 64 nodes, logistic regression classifier that really was not regularized or primed to reduce overfitting. We did use an LR model that was regularized to reduce overfitting, support vector machine and random forest. And random forest model overfit everything, so we threw that out. But we like the fact that the dense neural network performed well. The one layer 128 node model performed well, as did the regularized logistic regression classifier. So we use these moving forward for our outcomes testing. So if we look at just the dense neural network that performed the best and how this data is ingested, this would be 278 high-risk individuals. What you can see is that we wrote this program where we took the output of the model, took the number of visits that were predicted to be of risk versus the total number of visits for that individual patient over that 12-month snapshot, and then calculated this PI ratio. So the patient with the highest PI ratio had almost 100 visits in some shape, size, or variety over that 12-month span. And so 87 were deemed of high risk, so they had an almost 89% PI ratio. This, which is probably not easy to see, this kind of bar chart shows you the number of calls that were deemed to be low risk across these 46,305 visits for 278 individuals, which was about 2/3, and then the other 1/3 of the calls or visits that were deemed to be of high risk. So what does this mean, right? Tell me about real patients. So if we set up our PI index or risk ratio along this continuum of 0 to 1, and we say, how do known primary immune deficiency or immune disorder patients perform over this 12-month? Well, here are the PI index or ratios for a CGD patient who had been hospitalized, an AT patient who was in the outpatient setting but having medical complexity or related to ataxia telangiectasia, an XLA patient with cellulitis, a DeGeorge patient with a pneumonia over that 12-month frame. So you can see that these patients, not surprisingly with known IEI, do have some element of risk that's attributed and calculable via our model. But then we've got these patients that don't have a current IEI diagnosis, such as a patient with Evans syndrome, patients with neutropenia and syndromic features, and patients with developmental delay and fevers, who also fall along this continuum. So this is just showing you the output of this two-tiered step. First, patients that are deemed high risk with spirit analyzers. Second, patients that go through this machine learning stratification step that we would have a care coordination team look at and say, okay, maybe these patients with IEI need X, Y, or Z because we're having suboptimal quality related to their underlying disease. And these are patients that don't have a known IEI. Maybe they need to be seen by a clinical immunologist to be worked up. So now I wanted to show you some of the outcomes of the study. This is 3 years after our initial triage. So here are our initial baseline spirit assessments for high, low to medium, and no claim of interest. And then we wanted to look at the new primary immune deficiency diagnoses 3 years later, the number of hospitalizations per patient per year 3 years later, and number of urgent care visits per patient per year 3 years later. And what you can see is that statistically significant proportion of the high-risk individuals had a higher proportion of new PI diagnoses 3 years later, and a higher number of hospitalizations per patient per year. So higher number of diagnoses also increased healthcare utilizations 3 years out based upon our original spirit stratification. Urgent care visits did not quite meet statistical significance, but it was close. So we think we can stand on firm ground that the initial spirit triage and identifying patients with high risk does lead to an initial a higher proportion of PI diagnoses and a higher healthcare utilization rate at the 3-year mark. That's the spirit, the first step. How about the outcomes of our machine learning model? Busy slide, let me walk you through it. These are each of those 6-month assessments using 12 months worth of claims data, where we looked at the output of spirit, and then we looked at total cohort size. We did have some attrition over that time frame just due to migration in and out of the health plan, us moving patients from the general population into the high risk category. And then if we focus on just those high risk individuals, we broke those high risk individuals down into having a possible primary immune disorder, already under evaluation by a clinical immunologist in our system, having a known primary immune disorder, and unlikely to have a primary immune disorder due to a variety of factors. Maybe there was a motor vehicle accident, maybe this patient has secondary immunodeficiency that's clearly evident upon reviewing their chart. But the gold standard in breaking our high-risk patients down into these buckets was based on direct chart review. After doing this and reviewing the charts, we came up with, in this case, 37 individuals who were referral candidates, and these were the individuals that we could actually reach. So we looked then at those individuals who were referred versus those individuals who were high risk and not referred, and there was a statistically significant and meaningful difference in our PI ratio for those individuals who were referred versus those who were not, and it was higher. So we felt good about that. We felt that this metric could be useful in guiding referrals. Again, 37 candidates out of, in this case, if you start with over 3 years, 430,000 individuals, 16 that were referred. This is a manageable number to refer to any clinical immunology center or division over a 3-year period. Whereas if I told you I need to get 2,200 individuals in who are medium to high risk, that was going to be a challenge for anyone, right? So to close this part of the talk up, really what this is a risk prediction and clinical guidance system for that's validated for ascertaining risk and appropriateness of referrals. It hopefully will facilitate IEI patient identification and then reduce burden on the healthcare system by identifying those patients that are most appropriate for referrals. We want to make all of this freely available, so you can absolutely pull our code from our machine learning models from this GitHub repository. You can test and run the claims in your own environment. So we want to be very transparent. Of course, the Spirit Analyzer is made freely available by the Jeffrey Modell Foundation. So let's just shift gears. Got about 15 minutes. I'll go through this a little bit quickly because I do want to leave some time for questions. But one of the questions is just how do you assign a given infection or clinical event a weight of significance to say, the mental gymnastics we do as a clinical immunologist when we see a patient, we say, okay, these 3 ear infections in 3 months, are we worried? Maybe, but I'm not as worried about 2 pneumonias, bacterial pneumonias in 3 months. So what is the quantifiable weight that we can put on that? So we've mined weights from data and built this. I'm showing you a schematic of a Bayesian network here to help build a quantitative element around which clinical events or infections are most relevant to making an IEI diagnosis. And the way we did this is we extracted clinical events and diagnoses from a cohort and a control at Texas Children's. We set up conditional probabilities by really just calculating the prevalence in the disease cohort versus the controls. And then we extracted these concepts and then built them into this Bayesian network where the parent nodes are dependent upon the child nodes, in this case, disease probability versus manifestations. And so we ended up with 79 diagnoses that we thought were relevant that rolled up to 36 clinical concepts. So for example, let me just step back. A diagnosis might be bacterial pneumonia or H. flu pneumonia or pneumococcal pneumonia, and the concept might be bacterial pneumonia. So that's the way we structured it. Then we showed that our model was accurate and a validation cohort of 75 patients with known prime immune disorders and a medically complex control cohort. And what you see is that the output of our model risk scores did vary depending on the clinical journey, amount of data for the patient, but the risk score for the disease cohort was a little bit over 50, whereas it was around 6, the risk score for the control cohorts. This was highly statistically significant and had a 95% area under the curve. We didn't just ask this machine learning model to predict PI versus non-PI. We actually asked it also the most likely IUIS category, and it was about 90% accurate for taking the predicted PI or IEI subject and also ascertaining what the most likely IUIS category was for this individual, which, as you can imagine, could then get to pathway analyses, gene analyses in a patient who may not have a clear underlying molecular etiology for their disease, but has predicted IEI risk. Moving from EHR structured data, we've also been looking at unstructured text with natural language processing. And we have two different projects focused on this, where we take a cohort of controls and PI individuals. We extract the terms from the clinical note text. We do some statistical analyses of the terms and concepts, which helps us build an NLP or natural language processing machine learning approach that can either via manual annotation, thinking back to supervised learning, or a semi-supervised learning approach to understand different concepts that are relevant and weight them effectively for predictions about IEI risk or IEI relevant outcomes. And the ultimate goal here and hope here is that we'll leverage free text, which is highly rich, and valuable, and also generate new human phenotype ontology terms to improve phenotyping of these patients. This is just a high-level schematic of how we've approached our NLP work, again, looking at a control and a PI cohort, extracting, comparing the terms, and then quantitating those and learning. And this way we mine new features that we would not necessarily have learned from the structured EHR data, leverage the NLP system to go from this kind of maybe coarse, fuzzy, nebulous prediction about an IEI subject or patient to a more clear and granular, fine-grained prediction. So AI is great. The last part of my talk, I'll focus just in these last few slides on clinical informatics, because we can build great models, but in a vacuum, those aren't going to do anything. And that's why the mantra of clinical informatics is really that this is a handshake between technology, which is important, but it's probably only going to get you 20% of the way there. So the best large language model in the world that can do all kinds of cool stuff, ultimately, if it's not accepted by the people, the culture, and the values of the health system, it won't really help anyone. So, you know, AI is cool, but you know, this Ferrari is pretty rad. But if that's your car and your AI and that's your health system, you know what, that AI is not going to do well. It's not going to be sustainable in the long term. It's not ultimately going to make a huge difference for patients. So we do have to be cognizant of the many challenges associated with AI and how they balance into the culture and values and demographics of the population. We have to get our arms around risk, governance, trust, of course, privacy and security, bias and fairness, and really think about how these models can be implemented within a system that allows for continuous learning. And that really is the concept of a learning health system, where science, informatics, incentives, and culture are really aligned to improve care over time. And we're really moving from algorithmic development to understanding health systems, how providers, how physicians, nurses, and other members of the healthcare team interact with one another, and what works from an implementation science standpoint. So we're really focused on outcomes, rapid cycle improvement, and sustainment of these models, understanding this life cycle for clinical AI, for IEI, but for a variety of disease entities, so we can understand really within the health system how valuable these models can be. And ultimately, the end game is using a learning health system and these AI machine learning models within healthcare teams and systems to drive and facilitate precision medicine. So with that, good, we still have time for questions. Please, my email, avail yourselves of that. I'd love to hear from you. Again, I'm just really jazzed to be a part of this wonderful conference series. I'm tremendously appreciative of the invite. I want to definitely acknowledge my colleagues shown here at a variety of different institutions, and of course, always thank the funding agencies. So I am going to exit on my presentation so I can actually see you, and happy to take questions. Thank you.